In this video, we're going to look at simplifying difference quotients, that is, expressions of the form f of x plus h minus f of x over h, in cases where the f of x is a polynomial function. In order to do this, we first have to talk about how to expand expressions of the form x plus h to the n, where n is a whole number. This takes something called the Binomial Theorem, and it's a pretty scary looking formula. In fact, here is the formula for the Binomial Theorem. But we're going to demystify and deformalize this so that it isn't so overwhelming, and in fact, so that it's actually pretty easy for us to use. Let's start with deriving formulas for the first few powers of x plus h. X plus h to the first, of course, is just x plus h. X plus h, the quantity squared, is not just x squared plus h squared. Remember from algebra, this means x plus h, the quantity, times another quantity x plus h. And if we multiply this out, we've got to take x times both terms, and then we've got to take h times both terms, and we get x squared plus 2xh plus h squared. Hopefully that's a formula that's familiar to you from algebra. You may also have memorized a formula for x plus h, the quantity cubed, but let's look at where it comes from, because our goal here is to see the patterns that emerge. So this is going to come from taking x plus h, the quantity squared, which we just derived, times another x plus h. So we have to multiply x times everything. That's going to give us x cubed plus 2x squared h plus xh squared. And then we've got to multiply h times everything. So the first term is going to say x squared h. I'm going to put this right below my other x squared h term. And then we're going to have a 2xh squared. And then finally an h cubed. And if we add these together, we have x cubed plus 3x squared h plus 3xh squared plus h cubed. Now let's look a little bit for patterns that we are seeing. We've only got 3 examples here, but I think we can start to see patterns emerging. Let's start by looking at the x's. When we were finding x plus h to the third, the first term was x to the third, but the next term only had x squared, the next term x to the first, the next term no x's. That happened when we were squaring. X squared to begin with, x to the first, no x's. So the x's go down by 1. The power of x goes down by 1 as we move left to right across the expansion. H, on the other hand, does the opposite. We start with no h's, then h to the first, h to the second, h to the third. And the result of this is if we look at the degree of each term, it's the same as the power we're raising x plus h to. Third degree. X squared h to the first is a total of third degree. X to the first h squared, total of third degree. So if we're going to look at x plus h to the fourth, we'll actually derive it in a moment, but let's do some predicting. I'm expecting the first term to have all x's and no h's, x to the fourth. The next term will have 1 fewer power of x and 1 more power of h. The next term, x's go down by 1, h's go up by 1, so x squared h squared, and then xh cubed, and then h to the fourth. So to see where these numbers are coming from, let me write x plus h to the fourth as the quantity cubed times another quantity of x plus h. Now, there's only one way we're going to get the x to the fourth, and that's by taking x cubed times x. So we only have one of those. But x cubed h comes about 2 different ways. We get it by taking x cubed times h, but we also get it by taking the 3x squared h times x. Both of those products end up being x cubed h terms. So we have 1x cubed h plus 3x squared h. That gives us 4x cubed h. That came from the coefficients of the 1 and the 3. let's look at how we can find x squared, h squared terms. We can do this by taking the 3x squared h times h, but we can also do it by taking the 3xh squared times x. And so we have a 3x squared h squared and another 3x squared h squared. We end up with 6x squared h squared, and that 6 came from those two 3's. The xh cubed is going to come from taking the xh squared times an h and taking the h cubed times an x. And so we have 3xh cubed plus another xh cubed. We get 4xh cubed, and that 4 came from the coefficients in front of those two terms. And then finally, there's only one way to get h to the 4th. So plus 1h to the 4th. So let's take a look at what happened here. Let me rewrite our results in a form where it's kind of easier to see the patterns. So bear with me while I rewrite these. We had x plus h to the first is x plus h. We had x plus h squared is x squared plus 2xh plus h squared. We had x plus h, the quantity cubed, was x cubed plus 3x squared h plus 3xh squared plus h cubed. And x plus h to the 4th was x to the 4th plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the 4th. And we've seen the pattern in the variables, and we also, as we came up with that last row, saw to an extent where the coefficients were coming from. Let me just distill this down to just the coefficients. In the first row we have 1, 1. In the next row we have 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Those were the coefficients we have for x plus h to the 4th. This is called Pascal's triangle. You may have seen it before. And it's one of the ways that we can use to find the coefficients in the expansion of x plus h to the n. Now, I'm pretty sure in calculus you're never going to need more than x plus h to the 4th. You're probably not going to need more than x plus h cubed. But just to illustrate how really easy this binomial theorem is to apply, let's figure out what we're going to have for x plus h to the 5th. Let's do the variable part first. We know we're going to end up with an x to the 5th. The next term will be one smaller power of x, one more power of h, so x to the 4th h, x cubed h squared h cubed, xh to the 4th, h to the 5th. There's our variables. And our coefficients will come from this next row of Pascal's triangle. Remember, each row starts and ends with a 1. Every number in between comes from the sum of the two numbers up above it. So we'll have 1x to the 5th plus 5x to the 4th h plus 10x cubed h squared plus 10x squared h cubed plus 5xh to the 4th plus h to the 5th. Hopefully that makes sense to you and you actually have this process sort of under control at this point. So let's see what this has to do with difference quotients. Let's look at the example f of x is x squared plus x, and let's write and simplify the difference quotient f of x plus h minus f of x over h. Our first step is to rewrite this difference quotient using our function. And remember, f of x plus h just says look up at your formula for f of x, and every time you see an x, replace it with an x plus h. So I'm going to put this part in brackets. F of x plus h will say x plus h, the quantity squared, plus the quantity x plus h. I'll close the brackets. That is our f of x plus h expression. And then I need to subtract from this my f of x expression. That's just x squared plus x. So there's my f of x. And I have this whole thing over h. My next step will be to use the binomial theorem any place where I need it. So the only place I need it in this example is x plus h, the quantity squared. So that's x squared plus 2xh plus h squared. And then I have plus x plus h to the first still. I don't really need anything to simplify that. Minus brackets x squared plus x. Whole thing over h. My next step is to go through and remove any parentheses and brackets using distributive property wherever I need it. So I can just drop parentheses and brackets in this first part. But in this next part, and this is an important place where students sometimes make a mistake, I need to distribute this minus sign. It's like having plus negative 1 times it. So I have minus x squared minus x. Very common mistake is to forget to do that. Now we look for any like terms that we can cancel out. And this minus x squared has a plus x squared to give it a 0. And the minus x has a plus x that cancels it out to give us 0. And this should always happen in these difference quotients. Everything that was in the f of x expression should end up canceling out. And furthermore, everything that's left standing after we do that should have a factor of h in it. If that doesn't happen, you made a mistake, so go back and find your error. Okay, because everything has a factor of h in it, and because we can only reduce common factors, we're going to factor out that h. So we have h times the quantity, 2x plus h plus 1, all over h. We can reduce the common factor of h now, and we end up with the simplified expression 2x plus h plus 1. Let's try one more example together. Feel free to work along with me as I do this, or if you're ready, you can pause the video and try it and then resume to check your work. But we'll do this one together if you still need that help. So my first step is to write my difference quotient for the function that we have. So I have bracket 2 times x plus h, the quantity cubed, minus 4 times x plus h. That's my f of x plus h expression. Minus, I need my f of x expression, 2x cubed minus 4x, and the whole thing over h. Next step, remember, is to apply the binomial theorem wherever I need it. So I need to expand x plus h, the quantity cubed, x cubed plus 3x squared h plus 3xh squared plus h cubed. And then I have minus 4 times the quantity x plus h. And I have minus, in brackets, 2x cubed minus 4x, all over h. Next step is to do any distributing to get rid of parentheses and brackets. So we have 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed, taking 2 times that whole quantity that we had at the front end. I need to distribute the minus 4, so minus 4x minus 4h. That's the end of the brackets. And then for the next brackets, I have to change the sign of each term, so minus 2x cubed plus 4x all over h. And now I'm looking for the expected canceling out. There's the minus 2x cubed, the plus 2x cubed that cancels it out. The plus 4x and the minus 4x cancel out. Everything that I'm left with, I'll rewrite it here. You can skip this step if you want to, but I'll rewrite it just to sort of clean up what we have. Every term that I have left in the numerator has an h in it, so I can pull out that h. And we have the remaining factor, h times the quantity, 6x squared plus 6xh plus 2h squared minus 4 all over h. And then reduce those h's. And we have our answer, our simplified expression, 6x squared plus 6xh plus 2h squared minus 4. Okay, got it? Here's one for you to try. I'd like for you to pause the video, write your difference quotient for our function, use the Binomial Theorem, and then simplify it. When you're ready, resume the video and check your answer. Okay, are you ready? You back? This is what we should have ended up with. Pause the video again if you need to check through all of your work. I've put every single step in here. Hopefully you got this right.